This is the pattern you'll be able to implement by the end, which scans prompts for secrets and blocks risky calls. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Secrets in prompts are a real problem. People paste config snippets, deploy keys, or test tokens into a conversation for context. Then, a model call carries those strings into service logs, telemetry, or storage you don't control. A pre-flight secret scan stops that leak before it starts. The win is simple: blocked requests for risky tokens, clearer alerts for responders, and fewer emergency key rotations after a slip. The intuitive idea is straightforward. Before you call the model, run a fast scan over the prompt text. If a detector flags a pattern, stop the request and record the type. That way, credentials never leave your service or third-party telemetry. For short prompts, this adds almost no latency, but buys a lot of safety. We'll build a small pre-flight gate that inspects one or more prompt segments, flags common patterns like API keys, lets you accept known test keys, and halts calls when a high-risk token appears. It keeps LLM requests safe and gives responders useful metadata. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Start by checking a single prompt before any API call, so you can see how a detector behaves. This snippet quickly inspects a single prompt for credential spills before any LLM call. It imports Detect Secrets Scan module and opens default settings, which initializes the default plugin roster and ensures scanline mimics CLI behavior. Inside that context, scanline analyzes the prompt text and yields potential secret objects whenever detectors, such as StripeDetector, match the embedded sklive_. Wrapping the generator in list stores those potential secret instances, so we can safely access metadata like type, without ever surfacing the secret value or position. The final print confirms one secret and names its plugin, signaling the prompt would be blocked before reaching the model. Now try a small batch and restrict the detector set to reduce noise and speed up triage. This example batches 2 prompts and confines Detect Secrets to the StripeDetector plugin for faster triage. Transient Undersettings loads a plugin's used configuration, so only StripeDetector activates, keeping the scan focused on API key risks. Inside the context, a list comprehension enumerates each prompt and runs scanline, turning any yielded potential secret objects into truthy hits. Collecting the indices that produce hits means flagged points straight at conversations needing redaction, while safe prompts avoid extra processing. The printed flagged prompts list and plugin scope label verify that only the second prompt was stopped by StripeDetector. Once you can batch, you want to know which detector fires most often, so you can prioritize rotation and response. This snippet ranks plugin activity across contexts, so operations can prioritize the highest risk leak type first. Default settings initializes the full detector suite, and each context string passes through scanline to yield potential secret lists per source. Flattening those lists into types creates a simple catalog of plugin labels, which counter then aggregates into frequency counts. Using max on the type set surfaces the plugin with the most hits, and a follow-up count reports how many incidents it generated. The final print reveals AWS access key triggered 2 incidents, showing where responders should focus rotation effort first. After you know the noisy signals, reduce false positives by allow listing known test keys so they stop tripping the gate. This snippet shows how to allow list a known hash so repeated Stripe test keys stop tripping the gate. Default settings scans the legacy prompt first, and scanline returns potential secret objects, whose secret hash values we can keep safely. Those hashes populate the allow list comprehension, effectively mirroring a baseline of already approved test secrets. Running default settings again on the new prompt repeats the scan, but filters out potential secrets whose hashes were allow listed, leaving only fresh leaks. The print confirms 0 new blocks and 1 allow listed secret, proving the tweak cut noise without weakening protection. Finally, integrate the scans into your outbound flow, so the gate stops the LLM call when a high-risk token appears. This example finalizes the Preflight gate by scanning each outbound segment and halting the LLM call when a GitHub token surfaces. Default settings powers scanline over the segment list, yielding potential secrets whenever a detector fires. The comprehension keeps both segment labels and secret types, so on-call responders see precise alerts. Conditional expressions translate the leak list into status and response strings, keeping orchestration consistent for blocked versus sent paths. The print reports Preflight status equals blocked, with the tool segment cited, proving the guardrail stops the leak before the request leaves. In a real integration, this maps to middleware before the request serializer. Run the scan on each chunk of user input and on any system context you append. If a block appears, return a deterministic error to the caller and push a minimal alert containing the segment label and detector type. That keeps secrets out of logs while giving responders the metadata they need. Recap. This is a Preflight secret scan that stops API keys and tokens from ever leaving your service. Use it whenever you accept user-provided context or assemble system messages that might include credentials. One caveat: detector rules can produce false positives, so tune your allow list and plugin scope carefully. Next step, measure scan latency on your traffic. Then, tune the active plugin set and allow list strategy to balance speed and signal. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.